The last video is going to be talking about the normal model. So when distributions are unimodal and symmetric, we can often model them with a normal curve. So even if it's not perfectly normal, we can model it with a normal curve, and then we call it approximately normal. So that's something that's kind of important when we're describing things. We want to make sure they're described as approximately normal because the normal curve is actually a mathematical function and we're modeling it. So when we use a function to describe real data, we call the function a model. The normal model is centered at the mean and has standard deviation sigma. So n mu comma sigma is going to be how we describe normal models. So for example, um, IQ scores have a mean of 100 and a standard deviation of 15, and we model them with a normal curve. So for IQ scores, we would say it's normal with mean 100, standard deviation 15. So that's kind of what's going on with the normal model. It's we use it to approximate distributions that are unimodal and symmetric. When graphing a normal distribution, the inflection points, so that means that where it turns from happy face to frowny face or from frowny face to happy face, the vocab we use for that is concave up for happy faces and concave down for frowny faces. Or basically, it's like, would water run off or would water be caught by the cup? So these are the inflection points. Inflection points are somewhere around there. It's basically where it turns from frowny to smiley or smiley to frowny. That occurs one standard deviation above and below the mean. So this is the mean, mu. This is mu minus standard deviation, and this is mu plus standard deviation. So if we're going back to the original example that we had, where the mean is 100 and the standard deviation is 15 for IQ scores, this would be an IQ score of 100. This would be 115. This would be 130. This would be 85, and that would be 70, and so on. We use Greek letters to denote that they're not calculated from the data in a sample. Remember that parameters are what happen when we have the Greek letters, and that means that it's for the entire population. We use non-Greek letters or Roman letters like X and S to describe statistics, Latin letters, essentially. When we standardize data that is approximately normal in shape, we calculate a z-score. So we learned about z-scores before. Z-scores are great for comparing things that have unlike um, units, and they're not exactly similar in nature. We can also convert data to z-scores just to make it easier to understand normal distributions as well. So we can convert any data that's approximately normal to have a mean of 0 and a standard deviation of 1 using z-scores. And so my curve will look pretty much the same. It's just transforming uh, the, it's kind of doing horizontal and vertical stretches and stuff, just like we have done the rest of the year. But that's not going to change the shape of the graph. It might change how stretched it is or its location on the x-axis, but it's not going to change the actual shape of the graph. And so these transformations that we're doing to turn it into a standard normal, where we have 0, 1, 2, -1, -2, that's not actually going to do anything in terms of making something that wasn't approximately normal now all of a sudden magically it's going to look like a bell curve. That's not how it works. So it has to be approximately normal first in order to stay approximately normal with um, with a conversion to z-scores. 68, 95, 99.7 rule, also called the empirical rule. So if we have something that's approximately normal, then approximately 68.7% of the observations are within one standard deviation of the mean. Approximately 95% of the observations are within 2 standard deviations of the mean, and approximately 99.7% of the observations are within 3 standard deviations of the mean. So here's the mean, 1 standard deviation, 2 standard deviations, 3 standard deviations. My graph isn't perfect, and again, it's hard to draw on the smartboard. But what that means is that 68% of the observations are going to be inside the red shaded area. So within 1 standard deviation of the mean, I have 68% of the observations. If I extend this to be 2 standard deviations, 95% of the data will be between 2 standard deviations of the mean. And if I extended it to all the way out to 3 standard deviations of the data, that would be 99.7% of the data, or practically all of the data is within 3 standard deviations of the mean. There are very few that would be outside of that. Only 3 in 1,000 would be outside of that range, or that area under the curve. And so now let's do some quick calculations. Since we know that things are symmetric, if I'm looking at a normal curve and I want to find the probability that something is greater than the mean, I know that something being greater than the mean occurs 50% of the time. What if I have something that is greater than 1 standard deviation away from the mean? So what's the probability that something would be greater than 1 standard deviation away from the mean? Well, I know that just doing a little bit of calculating, I know that this is 50% from the mean all the way to the edge of the left, and in the middle is 68%. So if I divide that 68% by 2, there's 34% on each side of the middle. So I have 50% over here and 34% here. 50 plus 34 is a total of 84%, which means that the shaded region to the right of 1 standard deviation of the mean would be 16%. So a lot of this is just calculating and kind of understanding the symmetry of things. What if I want something between 2 standard deviations to the left and 1 standard deviation to the right? So here's the mean, 2 standard deviations to the left, 1 standard deviation to the right. So if I want to find this region, here's what I know. This is 68%. Then I have to figure out what this part is in order to add it. So this whole thing is 95%. And I basically would do, oh wait, 95% actually goes a little bit further than that. So that's my fault. So 95% goes to the 2nd standard deviation away. So basically, I have to figure out what each of these x's are, and then kind of figure out what this x would be. So I know that 68% plus 2x equals 95%. If I subtract this over, I get 27% equals 2x. So each x is worth 13.5% of the data. So since I need this x in order to figure out my shaded region, that's 13.5%. And so I add 68 and 13.5, and I end up with 81.5% of the data is in this red shaded area. So there will be questions like that that you kind of have to figure out. Suppose that birth weights of newborns are approximately normal with a mean of 7.6 and a standard deviation of 1.3. So I'm going to draw my normal curve, mean 7.6. You always want to draw this with a pretty accurate scale. 7.6, where it changes from smiley to frowny, is 1 standard deviation, and you kind of want them to be about the same distance, because if you're drawing it accurately, that's something that you want. So that's 8.9, 6.3, 5.0, 10.2, and so on. So that's kind of what's going on. What percentage of babies will weigh less than 89 pounds? So if I'm looking at this, that is everything to the left of one standard deviation. And so I know that this is 68%, and this all the way over is 50%. So that's going to be 50% plus 34%. So that ends up being 84%. What percentage of babies will weigh more than 8.9 pounds? Well, that's going to be 100% minus 84% because the whole thing has to be 100%. So I get 16% for that problem. What percentage of babies will weigh more than 5 pounds? If I want to figure out what percentage of babies are going to weigh more than 5 pounds, I'll make another quick normal curve. So 5 pounds is 2 standard deviations below. So I want more than 5 pounds. 95% are within 2 standard deviations, which leaves each of these on the outside to be a total of 5%, which means each of them is 2.5%. So this part that's unshaded is 2.5%, which means the probability or percentage that something is more than that empty spot is going to be 97.5%. Between which two weights will the middle 95% of babies be? That's 5.0 pounds and 10.2 pounds. What proportion of babies weigh less than 8 pounds? So here's the 8. Well, um, uh, I don't know how to do that, at least not yet. So, because we don't really have anything in the empirical rule for this means we kind of have to figure something out. So let's use z-scores. So the z-score for a weight of an 8-pound baby is about 0.31. So since it's between 0 and 1, that means that just based on knowing things, we know that we want babies less than 8 pounds. So that would be this area over here. It's definitely going to be more than 50%, but it's going to be less than 84%. So just using some logic, we can figure that out. So what we're going to want to do is we're going to want to either use a standard normal table or we're going to want to use the calculator. So what we're going to do is we're going to use the calculator. So let's go to second VARS. See how it says DISTER up here? That's normal distributions. We're going to use normal CDF a lot in this unit when we're trying to find things for approximately normal. Lower bound and upper bound, mean and standard deviation. So I want babies less than 8 pounds. So babies between 0 and 8 pounds, I know the mean was 7.6 and the standard deviation was 1.3. So I just calculate what it is and the calculator gives it to me. So it's 62.084%. Or if I'm writing it as a proportion, I'll say 0.621 or something like that. But we're in percentages at the moment. So if I go back and I answer this question, the proportion of babies, well, we're actually in proportion. So 0.6208 or 0.621 or so, 62% of babies are less than 8 pounds. I can also do this using z-scores. So recall that the z-score was about 0.31, or it's 4/13, 0.4 over 1.3. So I can calculate this using a z-score. So normal CDF. My lower bound is going to be, all I have to do is pick some negative number that's outrageously negative for the lower bound. The upper bound, I want to be 0.31 because that's my z-score. Mean of 0, standard deviation of 1. Now, since I rounded that to be 0.31, this is going to be slightly off from 0.6208, but it ends up being really, really close. And if I didn't round to 2 decimal places, if I kept more decimal places, it would be a lot closer to 0.6208. So I can do this using z-scores, or I can do this just straight up typing things in the calculator. So if I am dealing with this problem with oranges and their circumference, I'll call this variable x. X is the circumference of oranges. They're approximately normal with a mean of 20 and a standard deviation of 4. So let's quickly draw a picture. 20, 16, 24, 12, 28. So basically what I want is if we draw a picture, it's going to be way easier for us to figure out whether my answer makes any sense. So I want less than 18. So there's 18. So this is kind of what I want my picture to look like for number 1. So I'm going to show us how to do this again on the calculator. Let's go to, I'll show it both ways again. So normal CDF. I want my lower bound to be some negative number, or I can choose 0 because I'm not going to have a circumference less than 0 of an orange. My upper bound is 18 in this problem. So all oranges less than 18 centimeters. My mean was 20 and my standard deviation was 4. So that will give me 0.3085. I could also do this with normal CDF, saying that my z-score was -1/2, because 18 minus 20 is -2, and -2 divided by 4 is -1/2. So if I do this with z-scores, my mean is 0 and my standard deviation is 1. I'm going to get the exact same answer for my normal CDF calculation. So the area under the curve is 30.85% of the area. So 0.3085 is my proportion. Well, this is the same. I don't know why it's giving me 2 of the same question. What proportion have circumferences greater than 25 centimeters? So this is not going to be a very big number, because this is 20, here's 24, here's 28. So I want 25 to kind of be this number. So if I calculate this, I want to find the area under the curve. And from now on, I'm only going to do this one time. I'm not going to do it both ways. So normal CDF, I'll do it just with the mean of 0 and standard deviation of 1. So I want it to be bigger than 25. So 25 minus 20 is 5. And then 5 divided by the standard deviation of 4 gives me a z-score of 1.25. So a z-score of 1.25. Something greater than that ends up being 0.1056. So the percent or proportion of circumferences that are greater than 25 centimeters, 0.1056. What proportion has circumferences between 17 and 19 centimeters? So here's 20, here's 16. So I'm basically looking for this area. If I calculate z-scores, the z-score of each of these is going to be negative 0.75 and negative 0.25. So I want it to be somewhere between those. So normal CDF, negative 0.75 and negative 0.25. Again, you can just type the actual values in. So 17, 19, mean is 20, standard deviation is 4, and that would also work. So I end up with 0.1747 is this proportion. What's the 90th percentile? So 90th percentile is a little different. This is finding the actual value that this distribution has, finding the actual value that I need. So like finding the actual circumference value in centimeters. So what I'm going to do for that is inverse norm. So inverse norm, I want the area to be 0.9 because that's going to find all the area to the left. So 90% of the area is going to be to the left. Mean is 20, standard deviation is 4. I get 25.126. So 25.126 centimeters is going to be the 90th percentile of this. I also could find the z-score for that if I wanted to do it with z-scores. So mean of 0, standard deviation of 1. I could get the z-score that's associated with 25.126 centimeters, which is 1.282. So that would be how I do that. First quartile and interquartile range. So let's calculate both of those real fast. Inverse norm. So the first quartile is going to be at 0.25. I'll do the z-score of it really fast. That's negative 0.6745. But, oops, sorry. But let's also do it just with 20 and 4 to figure it out in centimeters so I don't have to do any calculations with it. So that ends up being 17.30. So 17.30 centimeters is the first quartile. The interquartile range, I could also find the third quartile at 0.75. So I could change this to 0.75. And I figure out that it's 22.697 or 0.70 if I rounded to 2 decimal places. Which I actually should round to 3 decimal places because that's what the class requires. And then 22.698 minus 17.302. As I'm looking at this, that's the interquartile range. I also could have figured this out because how far away is 17.3 from 20? So if I think about the symmetry of the graph, if I'm 20 minus 17.302, that gives me 2.698. So if I'm looking at the graph, the first quartile is 2.698 away from the center. So here's the first quartile. This distance is 2.698, which means the third quartile is also going to be 2.698 away from the center. And so that's just like logically what's happening.